Welcome to this lecture on reduced order estimator example. We will present an example for this approach. Now we have two pole placement approaches, polynomial approach and state space approach. How do these two compare? For this we will take an example from Ogata's book. We will try to achieve regulatory control of double integrator presented here. Let us discretize it with sampling time of 0.2 seconds. Here is the discretized system. Let us design a controller to place the poles at this location. Let us use the reduced order deadbeat estimator. Deadbeat means what? Both the poles are at the origin. First let us check that the system is controllable and observable. I would want you to try that out for this system. As mentioned in the previous slide, this is the example taken from Ogata's discrete time control systems book. The reference for this is given in the textbook. It is the regulatory control of a double integrator. We want the closed loop poles at 0.6 plus minus 0.4 j inside the unit circle. Here is the desired closed loop characteristic polynomial calculated here. Using Ackermann's formula given here, we can calculate the control law to consist of 8 and 3.2 as given here. We can check this with Scilab. So now we want to design the reduced order estimator and recall the A matrix as given here, B matrix as given here. This is the terminology we used in the previous lecture. We want deadbeat estimator, that is the eigenvalues at the origin, that is we want the eigenvalues of ABB minus LPB at 0. Notice that we have only two states, only one state is to be estimated and there is a scalar system. So we want it at the origin. So there is only one value at the origin. So Ek is a scalar, the error of the reduced order estimator, and hence this value itself is equal to 0. Because it is a scalar, its eigenvalue is that number itself, that is 0. So from this we can get LPB to be ABB minus AAB, which is this divided by this, that is 1 divided by 0.2, and that is equal to 5. So let us recall the reduced order estimator as given here. Let us recall the partition matrices from the previous slide. Let us substitute with LPB equals 5, which we derived in the previous slide. Substitute all of this into this equation. So we get eta hat of k plus 1 as ABB is 1, then LPB is 5, AB is 0.2 into eta hat of k. Then in a similar way we can substitute all the terms here and we get this second line, and for the third line we get BB as 0.2 minus LPB, which is 5, times BA, which is 0.02 of U of k, and you can see that this whole thing is 5, this becomes 0, this is 0, 5 into 1 is 5, I get this minus 5, plus for this factor I get 0.2 minus this whole thing is 0.1, So 0.2 minus 0.1 is 0.1, I get this expression. So let us rewrite this expression from the previous slide. Recall the control law that we derived in the previous video. Here is the control law we got a few slides ago. Now notice I have y from here and also from here. So this 8 into y, I get 8y, and this 3.2 will multiply this. Remember, this LPB is 5, so 5 into 3.2 is 16, 16 plus 8 is 24, so I get 24 here, and then 3.2 into eta hat, I get this. Let us substitute for eta hat from here. Now because it is eta hat of k, I have to subtract 1, so I get this expression. When I multiply this out, I get this. So 16 into y of k minus 1 minus 0.32 into u of k minus 1. This is the control law. Let us take the Z transform with 0 initial condition. So I get this 0.32 coming here to the left hand side. On the right hand side I have this. So when I take it to the right hand side, I get this control law. Let us also calculate by the polynomial approach. The state space expression is given here. When I take Z transform, I get this transfer function. Notice that k is equal to 1. Split this into good and bad factors. So BB is 1 plus Z inverse, BG is 0.02, AB is this whole thing which I have written in expanded form, AG is 1. Let us use the Aryabhata's identity. So we have to solve this expression. I have rewritten that identity here. On solving, I get R1 and S1 as given here. The control law is minus SC by RC. Recall the expression from the first part of this course. Here is the control law. When I factor it, I get this expression. This is identical to the control law that we obtained earlier. This shows that the polynomial approach implements deadbeat estimator of only the unmeasured states. Here is the Scilab code, _int.sce. We have placed the poles as given here, 0.6 minus 0.4. Here is the end of that code. Here is the output from Scilab, and we calculate RC and SC. I scale RC and SC. The answer is here. This is RC 1 and 0.32 Z inverse, and SC is 24 and minus 16 Z inverse. You can see that these values are identical to what we obtained earlier. To conclude, we presented a double integrator example from Ogata's book. We used deadbeat reduced order estimator. The state space pole placement controller is identical to the polynomial approach. With this, we have come to the end of this presentation. Thanks for joining. Goodbye.